So in the previous video we stated the implicit function theorem, and now we can start looking at the proof. So we start, as we always do, assume the hypotheses. So that means assume exactly these 4 bullet points here, that we have this C1 function of this type that maps xy's to n-tuples, and that we have this specific point in mind, x naught, y naught, where x naught and y naught are related by the equations that we think of f as specifying. And we have this invertibility statement about apparently a portion of the derivative of f. So my goal is to use the inverse function theorem to do this. Otherwise, I would have to redo a lot of the quite difficult work of proving the inverse function theorem. So we will do whatever it takes, even if it seems kind of difficult, to put ourselves in a position where we can apply the inverse function theorem. Even if it's difficult, it will be worth it, because proving the inverse function theorem was even more difficult than whatever we have to do here. Okay. So we definitely, with f, our function little f here, definitely the inverse function theorem has nothing to say about it at all, right? The inverse function theorem is about functions from r something to r the same something, right? So f is just of the wrong type. And so we are going to define a function of the correct type. Sorry, I think I misspoke when I said the domain of little f is r or whatever. It's actually E, this open set. So let's define capital F from E to r n plus m by, and before I say the definition, note that this has the correct type. So E is a open subset of r n plus m. So f is the sort of thing that the inverse function theorem might have something to say about. So define capital F by capital F of y is going to be, first of all, of x and y. So here we're thinking of this as being in Rn and this as being in Rm, right? So we're going to define it to be the following point in Rn plus m, thought of as a pair, again, of something in Rn and something in Rm. The first component will be whatever little f outputs. Little f outputs something in Rn. And the second component will be y, just y again. And this is for all points in E. So capital F is a version of little f that remembers what was the second input. So little f takes 2 inputs, x and y, and it gives you 1 output. Capital F is similar to little f, but it makes sure that whenever you input a pair, it remembers what the second input was. And the key of our proof will be to show that we can apply the inverse function theorem to capital F, then apply it, and then interpret the result. So right now, we want to show that the inverse function theorem applies to f. Specifically, remember the inverse function theorem is about a function at a point. So specifically, we want to show that it applies to capital F at the point x naught, y naught, which is the point where we assumed we had this information. That, first of all, that little f of it is 0, and this invertibility statement. So what we need to apply the inverse function theorem to capital F, so looking back at the hypotheses of the inverse function theorem, we need capital F to be a C1 function And we need, sorry, let me fix this sentence. We need capital F to be a C1 function, and we need that capital F prime at x naught y naught is invertible. So we need this to be invertible. Okay, so this is what the inverse function theorem requires of us. And then what the inverse function theorem will tell us, well, it tells us a bunch of stuff, but roughly it tells us that near to x naught y naught, capital F is invertible. And then somehow we want to use our local inverse for capital F to describe x as a function of y, to describe these little x's as function of little y. Okay, so I think I will split this into two videos. One video showing that capital F is C1, and one video showing that the derivative at x naught y naught is invertible. And then the following videos will make use of the inverse function theorem, which we can then use.